The broadcast is now starting. All attendees are in listen-only mode.
Hello, good morning, good afternoon. Welcome to the latest episode in our webinar series. Today we'll be covering RODI, high purity water generation systems. My name is Ed Simpson, and I'm the Director of Manufacturing Sales for Burt Process Equipment. In a moment, I will be turning the floor over to Mark Girgenti. Mark is the Director of Design, Engineering, and Business Development here at Burt Process and has been with us approaching 15 years. Today, Mark will cover the basics of high purity water systems, including the system basic components and preliminary design considerations. Please feel free to submit any questions during the presentation, and we will do our best to address all of them by the conclusion of the presentation. With that, I will let Mark begin today's session.
Thank you, Ed, and welcome everyone. I want to thank everyone for joining us today. As Ed discussed, we're going to be doing a webinar discussing high purity water systems, going through a lot of the basics, looking at a couple of case studies. And as Ed said, I do encourage anyone on the line who has questions to certainly type them into the question chat. We will try to answer all questions either during or at the end. There'll be another opportunity for questions. Any questions we don't get to during the broadcast, we will email responses to as well. There will also be a couple of polls throughout the broadcast today. They're optional if those would like to participate. They're going to cover a range of topics that we're going to be discussing here. So I want to thank everyone, and we'll get into it. Just a kind of a brief introduction for those who are unfamiliar with Burt Process Equipment. Burt Process Equipment was founded in 1970, and we are a worldwide leader in the design, manufacturing, and distribution of high purity and corrosion-resistant equipment and systems. We do work in the United States and North America as well as all over the world, with a focus specializing on obviously high purity water systems, pH neutralization, chemical feed systems, rain and reclaim water systems, as well as a variety of other technologies and distribution products. Many of these have also been covered in some of our other webinars, which you can certainly view as well. So now on to the topic at hand. Today we're going to be talking about high purity water systems. And I kind of use the term high purity water systems because there's a lot of different kind of nomenclature out there which is applied to these various systems. And here on your screen you can see a few different examples of what we're going to be talking about today, ranging from very large sort of RO-based systems, a semiconductor, to sanitary, to higher education, to general industries. High purity water is utilized in a lot of different applications. So a couple of kind of quick definitions as we get started here. One of the things people utilize a lot and kind of utilize it interchangeably with these systems is the term RO or DI or reverse RODI type system. I generally use the term high purity water system because it covers more of a variety of the type of, really the variety of type of systems we're talking about. RODI is really short for reverse osmosis deionized. And reverse osmosis and deionized are two very different technologies which we're going to cover today in a fair amount of detail. But to give you a high level, reverse osmosis is a mechanical filtration process designed to filter out total dissolved solids, whereas deionization is a chemical or electrical process designed to remove dissolved ions. So using the term, and I've seen this in specs and I've seen this in people in communication, RO, I want an RO system, I want an RODI system. Generally, we're referencing more of just a general high purity water system. And to be more specific, high purity water systems are generally broken down into targeting a specific water quality. And here on the screen, you can see on the right, here's a couple of the more common water qualities which are utilized. These are the ASTM, American Society of Testing and Materials, ASTM type 1, 2, 3, and 4. And there are subdivisions of these, ASTM type 1A, B, and C. And what you're looking at here, this is the type of different water qualities that you'll try to target within your process or your facility to achieve specific water quality. And there are many others, CAP, which we'll show in a second. And then, towards the end of the presentation, we'll talk a little bit about USP and WIFI, which is a pharmaceutical grade water system. RO and DI do contribute largely to the various parameters we see here. He was looking, for example, at ASTM type 1, conductivity, resistivity, but also things such as TOC, total organic carbon, sodium, chloride, nitrates, bacteria, endotoxins. These are a lot of the other parameters that need to be addressed when determining an overall water quality. What a lot of people ask me when I do design with various clients, what is really a high purity water system? A high purity water system is a series of processes designed to take your feed water quality, whether that's a city water source, a well water source, a reclaimed water source, and construct a series of processes designed to bring you to one of these water qualities, ASTM type 1, 2, 3, and 4 here. Or as an example here, the CAP, College of American Pathologists, which are utilized a lot, for example, in higher education and places like that. They follow a lot of the same structures as the ASTM, again, resistivity, conductivity, but also focus on some of the minerals as well as pH, which is also involved with some of these systems. So that's really what we're going to look at today is, taking a water quality, going through the various processes, why you do different things, how you optimize some of these different things to bring you to one of these different water qualities. And then when you get to the, more involved processes, these are electronic grade waters. This is the type of water that you would see in like a semiconductor fab, where you're targeting extremely pure water. And as you can see here, the list of items which we're targeting grows exponentially. So you have resistivity, you have TOC, but then you get into things like dissolved oxygen, particle ranges, very stringent bacteria requirements, and then a whole list of different ions. And this is what you generally refer to as ultra pure water systems. And we'll talk a little bit about these as well. They do follow the same basic parameters to meet, which we're going to talk about, to meet the ASTM and the CAPs, but these also involve a few other different technologies as well, which we're not going to get into too much today, such as things like dissolved oxygen removal and things like that as well. But this is kind of the higher end of making essentially ultra pure water. So what is typically involved in a high purity or RODI system? Well, most major components, most high purity water systems have the following major components. You have a pretreatment process, reverse osmosis system. This is generally referred to as kind of one section of your system where you're going to be doing what's called really your makeup water. This is the amount of actual pure water that you're going to make up in a given amount of time, which then feeds into your storage tank. Then from there, you basically have the break in your system, when this is really generally referred to as your recirculation or polishing side of your system, where you have your recirculation pumps that then either feed a loop or your actual processes, DI or ion exchange, ultraviolet, final filters, instrumentation, and then your actual loop piping, and then potentially EDI as well, which we'll talk about a little bit here. By no means is that set in stone. And as you kind of look at these different systems, you're going to see you can move some of these around to different sections, because again, what you're really trying to assemble here is a series of processes designed to move from a base water quality into more of a high purity water target that you're trying to achieve. So I use the general phrase when I kind of refer to pretreatment, because really the most important thing on your pretreatment train is ultimately your RO. Your RO unit, which we're going to talk about in a couple of minutes in great detail, does the majority of your treatment for your actual system because of what it is. It's taking out total dissolved solids. Everything really upstream of your pretreatment is designed as a means to allow your RO unit to operate more efficiently. And that can include things like particulates, carbon, water softeners, pH adjustments. These are all basically designed to allow you to optimize your RO for much higher efficiency.
Mark, real quick, how important is the water softening on that pretreatment in regards to the RO unit?
That's a good question, Ed, because, like I said, the pretreatment system is ultimately designed to facilitate, the efficiency of your RO. Water softeners are designed to remove things such as magnesium and calcium from your system. essentially, softening your water. The thing with an RO is how an RO operates, which we're going to get into here in a couple of minutes, is it acts by essentially removing those dissolved solids. The actual particles of calcium, magnesium, which your water softener takes out, will ultimately be taken out by your RO as well. The problem is when you begin to concentrate those particular ions in your RO unit, you run the problem that you'll actually get that scaling. So like everybody's seen hard water, for example, if you've ever seen it in the shower, you get that kind of calcium scaling that basically begins to occur. That's what will happen to your RO membranes if you don't have proper water softening or another means to actually basically remove that scaling component. You'll essentially end up with a calcified RO membrane, which will greatly reduce its efficiency and could potentially even over time cause the membrane itself to actually fail. So water softening is definitely one of the big ones that you want to look at as part of any pretreatment train, which is also why it's very important to have somewhat of an understanding of what your incoming water quality is coming into one of these systems. You can see what your hardness level is, what your chloride level is, because things like chlorine or chloramines, which are byproducts of just city water treatment, they basically put the chlorine in the water so it's disinfectant. When you concentrate that chlorine, you can actually oxidize your RO membranes, which is another reason why also the carbon filter or some other means of reducing that oxidation potential of your water becomes very important. And then obviously particulates as well. Based on the fineness of how an RO operates, you definitely don't want to be putting in anything with a lot of total suspended solids going into your actual system. And why is that the case? Because an RO membrane is a semi-permeable membrane designed to remove dissolved solids. A dissolved solid is any particle which is below 0.045 microns. And this includes organics, pyrogens, or things that actually cause viruses in the human body, temperature, fever increases in the human body, submicron colloidal matter, bacteria, different ions, for example, like might be just aforementioned calcium and magnesium. All of those things are a dissolved particulate that your RO unit is trying to remove. That's why I always say the RO unit is really what does the bulk of your work in a given system. And this is done by essentially applying a high pressure to your membrane, which forces the water across the osmotic gradient. So you have a filter here, which is catching these particulates, but at the same time, beyond just what a traditional, say, ultra filter would do, you also have this reverse osmosis gradient where you're pushing you're basically pushing water from an area of high concentration of dissolved solids to an area of low concentration of dissolved solids. And this is done by applying high pressure to your membranes. By doing this, you're essentially removing 95 and 99% of all the dissolved solids in your water. So if you go back to that, that chart I showed at the beginning where you're talking about water quality, all of those different items, majority of them are some form of dissolved solid. So if you so that's why the RO is so critical. It's going to get you 95 to 98% of the way there just by having a high efficiency RO. And then every process that comes after that moves you to that final step, essentially, of getting you to that target water quality that you actually need. So as I mentioned before, RO units typically use very high pressure, talking about 150 to 300 pounds of pressure. In the purified water is known as the permeates. The downside is because you are concentrating and pushing water from an area of high concentration to an area of low concentration, you do need a means to actually get rid of that high concentration water at that point. And that's what's referred to as the reject. And optimizing that permeate to reject recovery is really the kind of the nook of designing an RO system. Unoptimized, is a good rule of thumb because you have this reject stream. generally speaking, an unoptimized RO unit, for every 2 gallons of water you put in, you get 1 gallon out. You can end up with basically 50% recovery, which isn't very optimized, obviously. Generally speaking, you want to try to achieve as high a recovery as possible, which for the most part tends to fall in the 70 to 80% range as a realistic number of what you can actually achieve for your RO permeate recovery, or permeate at that point. And you measure this, and you measure the efficiency of the RO by what's referred to as percent reject. And this is 2 probes that basically monitor the conductivity of the incoming water and the conductivity of the outgoing water. And this shows the overall conductance difference that you should see, which is also referred to as the percent reject. As those numbers begin to drop, your RO membrane either needs to be replaced or needs to be cleaned. What I'm going to show here, and this is kind of getting a little bit deep, obviously, this is what's referred to as an RO projection. And I kind of want to show this just to kind of highlight what I was just describing, which is, how exactly an RO takes this different dissolved solids and brings you down. So when you're doing optimization of a lot of different ROs, what you want to look at, and you can add, this is why it's important to have your feed quality water, you can basically input, you can see here on the right, some initial parameters of what could be coming into your stream, ammonia, sodiums, magnesiums, calciums, some different anionic compounds, and then you have things like CO2, and you have a total dissolved solids. So here in your initial feed, you have 125 as an example. And what RO projection does, I can adjust the number of membranes, the array of membranes, which is if I'm going to have a membrane, I'm going to have, say, just membranes in series, or 2 membranes that then feed another membrane. And I adjust things like temperature and pH to really optimize what I get out of my actual system. So down here you can see what the different concentrate stages are. So this is where I take this is what's really your reject stream, which here goes up to 552 ppm of total dissolved solids. And this is my permeates, which takes my 138 and then drops it all the way down to 1.11 there. And you can see the rest of the parameters as well here on the right, all drop when you have an optimized RO unit. In this case, it's a 2x2x1 array. One of the things to note, I do get this to come up a lot, is what's a good temperature for the water to run through an RO system. Most ROs that you see online, for example, they're just advertising kind of generic use ROs. They always rate them at 70 degrees Fahrenheit for the water to come in at, and that's not actually an ideal range for an RO to operate at. You generally want an RO to operate at a lower temperature. The lower the temperature, the more the membrane constricts, and actually the higher the permeate quality that you get out of it. At a 70-degree temperature, your RO membrane is more open, which increases your flow rate through the system, but doesn't actually give you the greatest permeate quality. So that's why you can see here, we're going to run this one at 55 degrees. So when people talk about, an RO system, generally speaking, you actually want to cool the water going into it, if possible, if practical, obviously, as a means to get a higher permeate quality out of your system. And you can see here, this is the permeate flow of 45. The feed flow is at 60 GPM, here the raw water feed. The reason that this number is actually higher at 75 is because you always take a portion of your reject water and bring it back into your RO feed. That's why the actual feed flow is at 75 GPM as opposed to just at 60 GPM. And the pressure in this case here is 230 PSI. Looking at it schematically here on the right, you can see that's one of the RO units in the lower left hand and lower right hand corner. There is one of the heat exchangers which is utilized in these systems. And this is what an RO system looks like. Looking at it from a P&ID perspective, this is actually the same P&ID. The one on the left is zoomed in. This is your high pressure pump, which again ranges 150 to 300. In this case, is in the 230 PSI range. This is your RO membranes here. This is your 2x1x1 array. So the water comes into the first set of membranes, the reject of those gets put to the second, and then the reject of the second to the third. Then you have your combined permeate stream here. This is your percent reject. These two here, this is what you're actually monitoring, your percent reject across the RO. And then you have a drop here. This is actually your reject stream at this point. Looking at the blown up version, the only difference here is you can see this actually has a preheat exchanger on there again. The bigger your RO system, the more you want to try to optimize its performance as much as you can, because reject water is essentially a waste. You're taking your city water source, you are taking your your well water, whatever your water feed is, and you're going to be sending 50 to 25%, maybe 20% if you're optimized down the drain, essentially. So it does become fairly critical in that regard to do that. If you have, for example, say a 50 GPM system, you're always dumping 10 GPM down the drain, as long as that's being utilized in that case. So it's very important to definitely want to optimize your RO in larger systems. Moving away from RO for a second, like I said, ROs, they do the bulk of the work in the system, but they only get you 95 and 98% there. So as a comparison, a lot of people like to use the term, what is the resistivity coming off of an RO unit? Probably 0.1, 0.2. It's not that high realistically, because you still have a lot of those dissolved ions, which will go across the osmotic gradients. So you do need to look at, so you probably have like a 1 conductivity essentially coming off of your RO system. To really achieve that higher level of resistivity with it, depending on what your target is, ASTM type 2, for example, is 2 mega ohm, type 3 is 4 mega ohm, type 1 is 18, 18.3 is the theoretical limit. You then need to go into some form of a polishing step, whether that's a which is some form of deionization at that point. So, in a high level, deionization is essentially a process whereby I am pulling or removing the various ionic content from my water.
Hey, Mark, another quick question. I know you're getting into the ion exchange now. I don't know whether you'll cover this now or later, but we get questions a lot on when do you use, an electro deionization as opposed to a standard, mixed bed resin bottle in an application?
That's a good question, Ed. And it really does depend. And we're going to talk about some of the different ion exchange as well as the EDI, as traditional deionization exchange, as well as EDI here in a couple of minutes. But they kind of both have their place, and they can both be used, essentially, and also can be used together at different points. So we'll kind of come back to that in a second here, but most people generally still use base deionization. Base deionization is taking a form of a resin, which will actually pull some version of the different ions out. You can see a few here, cations versus anions, calcium, magnesium, sodium. These are all basically either cationic, chlorines, bicarbonate, nitrates. These are all the anionic streams. And regardless of the method you choose, you're going to get the same basic results. I'm going to talk a little bit about deionization first, then we'll talk a little bit about EDI, and then we'll kind of do a bit of a comparison between the two of them. But what is just deionization? Well, deionization is essentially you have what's basically referred to as a resin bead. And on that bead, you have, if it's a mixed bed resin, which means you have both cationic sites and anionic sites, or positive and negative sites on that resin, it's going to target different species, whether that be sodium or whether that be bicarbonate. It's going to essentially replace it with either a proton, which is an H+, or a hydroxyl, which is an OH-. The byproduct of the exchange then leads to the formation of just basic water. So I'm essentially pulling out these two charged particles with both anion and a cation, and I'm going to end up with a neutral species of water in that case. Traditionally, ion exchange is done in a lot of different sizes. The most common is probably a 3.5 cubic foot resin bed. And what happens is the water enters, and because it's basically based on channeling and contact time for standard high purity mixed bed, this affords you about a 10 GPM per 3.5 cubic foot resin bottle. The downside of traditional chemical resin is it has an exhaustion. You have a bottle that's basically full of these resin beads, and over time, what will happen is you'll have what's called exhaustion. You will have basically exchanged all of the different positive and negative or anionic, cationic, anionic sites within the resin, and thus you'll end up in a situation whereby you then have to replace your bottles at that point. So that's the debt, and then replacing that resin is obviously a cost. The resin itself, while not hazardous, does have these ionic species in there, and then needs to be regenerated. That regenerated process involves the use of acids and bases. So it is a bit of a messy thing. It does require a fair amount of service, and depending upon how much pretreatment you've done upstream of this, your resin can exhaust very quickly. Traditionally an ion exchange bottle may last, with proper design up front, maybe a month. Without an RO, a resin bottle can be used up in a day, essentially. An EDI system, on the other hand, essentially uses electricity to basically pull, by electrical field, to pull anions and cations out of the water. There's no actual exchange sites. There's no actual resin. You do end up with a small reject stream, but unlike an RO, where it's 25%, it's only about 2% of the water in this case. So you're passing essentially a high voltage current to these different anode and cathode plates, and you're pulling the ions basically out of that stream at that point. The nice thing about EDI is it's not really a chemical process, it's actually an electrical process. And there's no resin, there's no regeneration of resin. The downside is the EDI takes a fair amount of additional controls. You have to have there's definitely programming that goes into controlling the control voltage, and it is fairly high power consumption. Something even as small as, say, like a 3 to 5 GPM EDI can be pulling off of a 30 amp 460 volt three-phase power feed. So it does require a fair amount of electricity to actually remove that EDI from the system. That being said, as a comparison's sake, and we have a question here. So CEDI versus EDI, they're actually the same thing. CEDI just stands for continuous electro deionization. EDI is just a shortened version of electro deionization, but CEDI and EDI are the same thing. By comparison, but if you look at comparing the two, EDI versus DI, they both have their pros and cons. EDI has a lot of upfront cost with it over, say, just buying a basic DI bottle. And it does have some level of additional power consumption, but long-term, from a service standpoint, DI is going to be much more expensive as you have to keep swapping out bottles. Making EDIs that go on larger flow systems, if you have to put it, for example, in the loop, can be very expensive upfront capital equipment-wise, whereas a series of DI bottles would be less expensive. If you're only doing deionization on the pretreatment side of your system, say coming off of your RO, EDI is a very practical solution. It eliminates the need for the DI resin beds. And coming off of a single EDI, you can generally raise the resistivity up to about 15 to 16 mega ohms at that point, just coming off of just one EDI. So it does have a lot of advantages in that regard, particularly if you don't want to deal with the hassle or the nature of having to deal with regenerating resin beds. When you get into very high-end water qualities, you also generally combine the two of them. So very often, you will end up using an EDI in combination with a DI to achieve that 18 mega ohm water that you're trying to achieve, either as a part of an ASTM1 or as part of an electronics grade system at that point. Moving away from the RO, the EDI, talking about just TDS and conductivity, resistivity, there are a lot of other parameters that come up on those different systems, such as bacteria, endotoxins, total organic carbon. And these are addressed by some of the additional technologies that we're going to talk about here, one of which is UV or ultraviolet lights. So at a high level, ultraviolet light essentially passes a wavelength of UV light through your water or wastewater as a means to do some form of treatment. And There are two primary types. The first one is 254 nanometer UV, which is utilized to basically kill or inactivate microorganisms. So again, you do take out a fair amount of bacteria in your system with your RO, but your water itself on the kind of the polishing side, this basically helps mitigate the bacteria that's still present or could be forming within either your distribution or polishing loops. One of the downsides of having like a resin bed is this is now basically your water's passing through essentially a block of granulated material, and anybody who's ever owned a fish tank, if you have that charcoal filter in there, in time it will turn green. It's just a very good site for bacteria to grow, even if water is still moving through it. So a UV light is very critical in maintaining that bacteria level initially within your actual system. A 185 nanometer UV light, on the other hand, is a much shorter wavelength. So whereas 254 nanometer, you can see here on the right the different wavelengths. 254 nanometer is really a short wave UV, whereas 185 is a vacuum UV. It's much higher wavelength, and it's designed to break up TOC or total organic carbon. This is a very common parameter in chemical and semiconductor applications where you want to get rid of essentially that carbon backbone chain which is present in your system. TOC is removed by the RO, but that'll generally drop you down to maybe 50 to 100 parts per billion. The 185 nanometer TOC UV can drop you down to say the 5 or even lower levels of TOC required for some specific water qualities. It is worth noting that the two of them are not interchangeable. So the wavelengths work at specific levels just basically because you're talking about things in the quantum realm at this point. But 185 nanometer UV is not necessarily a straight peak, where 254 nanometer tends to be a much more linear peak just at that wavelength. You do get a small 254 nanometer peak in a 185 nanometer UV. Thus, if you have the choice of only being able to put in one UV, a 185 nanometer UV will give you some of the 254 nanometer wavelength as well, in addition to 185. So it can be beneficial for both bacteria and TOC destruction, assuming your bacterial levels are not that critical at that point. Because ozone is used sometimes in the system, either to sanitize the tank or as part of an overall loop sanitization, you also can use a UV light to destroy that, and that's typically done with the 254 nanometer UV, which is used to neutralize the UV light, the ozone, which is present in the water stream during its recirculation process. And then finally, kind of downstream of the DI, as well as the UV, you have your final filters. These are generally 0.2 to 0.5 micron, and they're designed to remove endotoxins. Endotoxins are basically the biological residue left from the bacteria, which is destroyed by your UV, as well as serve as any kind of a final catch, essentially, for anything from your resins that may be coming out as part of your distribution or recirculation loop. As we kind of talked about earlier, high-purity water systems are divided between two major areas. You have generally your pretreatment RO side, which may or may not encompass part of your DI treatment, and then you have your loop and your polishing side. And the storage tank is kind of the break point between the two of them, where you have your generation or makeup rate versus your recirculation or distribution rate. And for high-purity water systems, the storage tank, its sizing is not super critical. A lot of times people like to say they want to store a lot of high-purity water. That can be challenging at higher water quality just because it's very hard to keep a large volume of water very clean, even when you have a recirculation going on in your system. And actually, when you get to very high water qualities, you generally want this tank to be very, very low as far as an actual volume is concerned. These tanks do tend to be thermoplastic in different applications, such as pharma. They can also be a polished stainless steel, and they are generally sealed off to the atmosphere. They may even have things like nitrogen blanketing on them, and they have a vent filter, 0.2 micron hydrophobic, which is designed to prevent, when the tank is going either through a filling or a vacuum process, when they're pumping down, any kind of particulate from entering them. So essentially, you're trying to create a clean environment here as you have that filling and distribution and recirculation going on within your actual system. One kind of aside I wanted to mention before we kind of talk about the loop and get into a few case studies here is RO reclaim. You're seeing this a lot more as you know, as people are becoming obviously more environmentally conscious, and we've mentioned ROs do have a reject stream. There's really nothing wrong with that water. It's essentially just a very concentrated form of city water. And people are beginning to look at new uses for that water, particularly things just, you know, as a means for either, you know, as basically a reclaimed water source. It's not something you can use as a potable water source at that point, but more and more municipalities are requiring you to at least try to reclaim some of that reclaimed water, because again, in very large applications, it can be a significant amount of water being sent down the drain at that point. So these are fairly basic systems, and they can be utilized for a lot of applications: irrigation, flushing fixtures, even potentially cooling tower makeup in the right situation. So it is worth noting that there are things going on with RO reclaim, as well as some of the other reject streams, such as even from the water softeners and even some of the backwashable carbon beds as well, to make these systems a bit more environmentally friendly in that regard. We mentioned a little bit during the RO section about some of the instrumentation which is involved in these systems. Obviously, resistivity, conductivity, which are just basically inverses of each other, are often utilized on the RO system to monitor percent reject. They're also very often installed on the loop feed and potentially the loop return as well to monitor the quality actually going out to the various processes that you are feeding. Pressure is often utilized. Many times these pumps that are utilized on the distribution side of the system will be on VFDs. And this can be used obviously as a means for the VFD control, flow sensors on either the RO feeds or the distribution feeds. And then you get into some of the more higher end monitoring, such as TOC. TOC can be monitored real time by means of a sampling within your actual system. And then you can move on from there to do some more elaborate ones as well, such as things like dissolved oxygen and silica sensors, when you get into more of the ultra high purity water realm. But your system will have a lot of these different instruments, which is why systems also tend to be PLC based controlled, because you are controlling a number of different processes which are working together. So now we've talked quite a bit about some of the different technologies that go into these systems. Obviously, if you're making a high purity water stream, you need a method of delivering this water, which also then allows you to maintain that water quality to your points of use. And this is where you tend to come up with what's referred to as a recirculation loop. If you generate high purity water, 95% of cases, your water is not just going to sit stagnant in your tank just to be distributed out by use. It's going to be constantly recirculating through some form of a loop. And that loop will also be tied into your polishing, which will have your deionization, UV, final filters, some of the other processes we just described, as a means to maintain that water quality. And there's a number of different ways to design a loop, and there's also a number of different materials that are involved in designing a high purity water loop. Majority of loops are either what's referred to as a serpentine loop, or what's sometimes been coined a ladder loop. And a serpentine loop is essentially one long loop, where you come off of the end of your treatment processes, you go out to your various various feeds on one single pipe run and then come back to your storage tank. It's very commonly utilized in smaller loops as well as in industrial settings where your high purity water process is only feeding maybe a couple of critical different tools or systems. More commonly, when you're looking at more of a lab building structure, you tend to look at what's referred to as a ladder loop. In a ladder loop, you have a primary feed and return loop, and then basically on each area or each level of your building, you essentially break off of that into smaller subset loops that allow you to basically regulate and control the flow at each of the various loops while still having your primary feed and primary return loop. And I'll show you guys an example of that here in a minute. Talking about materials for a second, For lower quality water systems, RO, boiler makeup, humidifiers, PVC can certainly be utilized. Anytime you get into the realm of more high purity water, such as an ASTM or CAPS type based system, you generally want to go with either a polypropylene or a PVDF based system. Polypropylene, either natural or the European color socket or fusion, is both acceptable. There isn't much of a difference, and I'm not a piping guy, but there's between alpha and beta nucleated, there really isn't much of a difference there from an actual cleanliness standpoint. And it's probably the most commonly used material is going to be a socket or a butt fusion European polypropylene pipe. PVDF can be utilized. It does serve two primary purposes. The first is PVDF is plenum rated. So if you have to run your loop in a plenum rated environment and you have to go thermoplastic, then PVDF is one you definitely want to consider. And it also has the ability that it can be sanitized quite frequently. It has a higher chemical resistance than polypropylene, either pigmented or not. And then finally, on the sanitary side of the system, you have both a natural and PVDF SIB or bead and crevice free. And what this is basically a form of joining the pipe where you essentially have a diaphragm in your welder, which causes a very smooth weld within your actual piping loop to basically eliminate any of those rough surface areas caused by just either natural or socket fusion process. In pharmaceutical applications, you also see stainless steel. This is typically a polished stainless steel, which is also passivated and orbital welded, and that's used really predominantly only in the pharmaceutical industry at that point.
Thanks, Mark. Hey, another real quick question. You mentioned sanitization, and certainly our field service department does a lot of sanitization procedures, either at startup when the systems are installed or on a semi-regular basis. Can you touch on why that sanitization is done and how often that should be done?
Of course. Yeah, I mean, so I mentioned earlier, I got mentioned a couple times sanitization. I mentioned bacteria in the system. Anytime you have a water source, even when you have a recirculation running in your actual system, in your loop, it's still an area where you do have, and you can even see looking at some of these different pipes, there is going to be some kind of roughness within that pipe. And regardless of the velocity you choose, even though you do want to maintain a turbulent velocity through your loop, you do run the risk of bacterial buildup in your system. Now, you're not talking about a large amount of bacterial buildup, but enough that it will affect your overall water quality. And that's really the determining factor in when you want to sanitize. Sanitization is either done either by chemical or by a thermal means, the most common, of course, being chemical. And ozone is typically the most common. The reason ozone is utilized is, as I mentioned, in the UV section, it can be destroyed by the UV lights present in the system. So, the UV naturally purifies bacteria in the water to a degree. Basically, the sanitization of the loop maintains the bacteria of the entire water system at the various points of use. So, if your bacteria spec is very high, you generally need to sanitize very frequently. At a minimum, even for a lower grade water system, you probably want to sanitize about twice a year. And if you're talking about a higher level bacteria requirement, you want to sanitize probably several times a year. In the bacteria field, they'll do sanitizations every day because that's how critical bacteria and endotoxin buildup is in that various industry. And the sanitization process system is generally still running. You just bypass your DI lights and bypass your DI bottles, and essentially the water basically is a low concentration, maybe like a 2 ppm level of ozone overnight, and then the UV lights are turned back on, and it basically just turns the ozone back into oxygen at that point. There are a few other chemicals which are utilized, but ozone is by far and away the most common at that point. And again, it's something that needs to be done as part of a routine maintenance for any loop design, to function properly. So I mentioned before a little bit about what a loop looks like, and here you can kind of see, this is just kind of an example showing kind of a very large loop, obviously, in this case. And looking here, this is your base system, and this is what I mean by a ladder loop here. You see you have a primary feed going up and a primary return, And at each individual level, you kind of have these sort of smaller loops here. That's really what I refer to as like a ladder loop in that case, where I'll have, say, like a 2-inch primary feed line, and then I'll break down each one of these floors, sizing it based on what my actual flow rate is. That's actually the requirement. And this might be like an inch or inch and a quarter line there. So as an example, if I have like a 60 GPM loop, each floor here in the system might only see like 10 or 15 gallons a minute at that point. This helps you kind of regulate and control the pressure at each individual floor. More of an example, like a serpentine loop is kind of like looking over here, where the water just kind of comes out and just sort of comes back in like one primary loop. It's not very practical if you were to run this loop, say, as like one giant loop. Every one of these floors would go back and then forth back, and then you have this very large loop running through, very large diameter loop, running through your entire building at that point. So there's definitely practicality designing your loop with more of like a ladder loop design at that point. And one of the questions that does come up, particularly in the process and plumbing, is kind of how do you really pick a flow rate for these systems? And there's two factors to consider when looking at a high purity water loop. One is obviously what your use is, and you can apply things like diversity to that if you're looking at different, say, fixtures or different processes, how much water you actually need. But you also need to build in an additional value into your system to allow you to maintain a turbulent flow in your system. So because you don't ever want to get the laminar flow. You generally want, 3 to sort of 6 feet per second of actual flow running through your loop at any given time, even during a period of high use. So while you're looking at your various fixtures, you may only see an actual usage of 15, of like me say 40 or 45 GPM, your loop will run closer to say 60 to 65 GPM at that point. In addition to that, this is kind of highlighting what I was just thinking about the 60 GPM. This kind of shows some of the various, when you have different pipe sizes, you have different flow velocities, for the 1/2 inch. This is kind of where you want to be, this 2 to sort of 1.5 inches. And then you got to look at what your various turbulent flows are at the same level. This is how you want to look at really sizing that sort of velocity in your loop to maintain good efficiency within your actual system. It's just an example here using polypropylene. And then you have to account for, the pressure drop across your system. That's how you're going to size your actual loop pressure. So you need, X amount of pressure, say 30 at your various processes. Then you have to look at what all the different delta P's are. And this is just giving you as an example. Obviously, this is a fairly involved process we're not going to go into in great detail today. This covers, 2-inch diaphragms, 3/4 inch, various different valves. And this will vary based on your material that you're going to use, whether that be stainless steel or thermoplastic in this case. And then it actually shows you here, what the actual pressure drop is at various flows. So, total pipe pressure at 60, based on 1,220 feet of pipe at 2-inch, elbows, different valves that are involved. The elevation difference, back pressure if you have a spray ball in your system, and then your overall PSI requirement, somewhere say around like 97 PSI. This is an example in this case. If you're either a plumbing or a process engineer, this is the type of exercise that you're going to need to go through to properly size the pressure, in addition to comparing that to your actual flow going through your system. So I kind of want to sort of take everything we just talked about here and kind of roll it together, showing you guys kind of like just one example here. This is a semiconductor fab, so case studies. You're looking at a system that's a little bit bigger, but it kind of highlights all the different technologies that we've talked about so far in this webinar, and it really does kind of show how these things really kind of go together. So again, start with, what your water quality is. In this case here, this is what we're looking at, 18 megaohm, 5 TOC. And we're going to build up a series of processes here from our base water quality, determine how we're going to get to some of these different levels. I don't know why that's doing that again. Okay. So again, this is the RO projection from before, and this was just showing this earlier. This is the RO. Obviously, we talked about this in great detail, whereby we're going to really do 80% of our work in our system, 98% of the work in our system to achieve our water quality targets. Again, low TOC, very, very high resistivity values. The projection here, again, is a 2x2x1 array. And from a P&ID standpoint, this is really the pretreatment in this case here. They're coming off, this is just city water booster because of pressure. You have your multimedia beds for particulate removal. You have your chlorine removal here. There's actually a metabisulfite injection in this case. You have your water softening to soften your waters, we discussed in great detail. And then this here is just your brine tank is located down here. And then this is your chemical injection. This is common on larger ROs where you want to be able to actually clean the membranes or disinfect them during actual operation. And then we have our heat exchanger process, which then goes into our primary RO for treatment. So this encompasses the pretreatment as well as the RO portion that we were reviewing earlier during the webinar. You can just see larger. And then we move into our storage tank. And in this case, we'll be able an RO break tank as well as a DI break tank. So we're going to come into our RO storage tank. This is your vent filters, conical bottom generally, because you don't want to have any kind of a water buildup or any kind of stagnation in your system. This is your loop return, your spray ball. This is just a drain over here, and then you have your primary suction. This goes into your distribution for your RO water, which goes through UV and then has its own separate loop out. And then this begins to feed your DI process. This is an EDI system here. That's your small reject, which we discussed. And EDI itself also essentially has your monitoring similar to RO for percent reject, where you're going to measure the various resistivity on both the feed as well as the discharge from the EDI system. This is your DI storage tank. Again, here you can see this has got the feed. This is your nitrogen blanketing here, final filters. This is a built-in ozone system. In this case, that's what that would look like if you're doing sanitization of your system. You can see they've been dissolved into the tank here. And then it feeds into your distribution system. You have your 254 nanometer UV here for ozone and bacteria, your DI monitoring the resistivity for exhaustion, and then your two sets of final filters here as well. So even though this is making a very high water quality, it does essentially show in all systems basically to some degree or another have this sort of integral different components to basically design your come up with a proper design for your high purity water system. I want to end off here talking a little bit about the differences. We talked a lot today about obviously high purity water. We talked a lot about ASTM, CAP. There's a whole other side of this, which we're going to touch on very briefly, which is the life sciences side of high purity water systems. And you can see kind of an example there. Life sciences for high purity water is kind of its own little, it's got its own little requirements. It's less concerned about things such as like I said, resistivity, TOC, and it tends to focus really between two different parameters, USP, which is US Pharmacopeia, and then WIFI, which is water for injection. And as you can see here, the water parameters are a bit different. For USP 24 purified, you're looking at 1.3 microsiemens, which is like 0.1 resistivity, as opposed to the one we just looked at where you're looking at 18 mega ohm. Obviously, bacteria is still a concern, TOC. These systems tend to be much more focused on things, less on just more on bacteria concerns, endotoxin concerns, and then also, some of the various minerals, as opposed to things like resistivity. As such, you don't tend to include a lot of deionization in these systems. In USP Pharmacopeia, now can be done with an RO system, but generally WIFI water can only be done with a sanitary still. So it uses a very different technology than what we presented so far, as a means for actual treatment. In addition to that, they also need to be sanitized, as we talked about earlier, very frequently. Sanitization of these is generally done with either steam or hot water as opposed to chemical, and they're all generally stainless steel. You can see here the thermoplastic tank being fed by all sanitary stainless steel in that regard. In particular of USP and WIFI systems is a requirement for validation. And validation is essentially a testing process that high purity water systems for the pharmaceutical industry go through, which basically certify them for use in drug manufacturing. And those tests vary considerably from, weld mapping, weld testing, spray ball testing, and a number of different items as well. To basically prove the validity of the system. You don't tend to see that level of validation with other types of systems. They will be rigorously tested, of course, but this is kind of a specialty to the life sciences industry. And this is just one example here. Again, very similar. You have more of a sanitarily designed stainless steel storage tank here. This is actually off of a loop that already exists. And they're just doing some local polishing, in this case, sanitary tea-style filters. Again, in this case, sanitary design and bacteria really begin to become the primary focus of these different types of systems. And just a 3D model here. Almost all these systems, by the way, are actually designed in 3D, which can be obviously utilized quite a bit when it comes to BIM, as well as Revit design when doing actual building designs and layouts. So that concludes today's webinar on high purity water systems. We will be doing our last webinar series of the year on December 9th, where we'll be talking about containerized and modular design of systems. This will be discussing how some of the various systems that we build are utilized and built into mobile and or containerized systems for installation at a client site. So if you have interest, it is now open for early registration. And I want to thank everyone for joining us today. And if you have any additional questions, certainly feel free. We'll be on here for a few more minutes. And we do have a few questions already. And again, any questions we don't get to now, please feel free to email myself and we will respond to all questions. We will be sending out a survey after this as well. And there also will be made available a recording of this video for anyone interested in it. Do you have a few questions here? What are the steps required for expanding a loop or adding to an additional flow capacity to an existing system? I get this question a lot. So this is, if you've already designed a system, and you have a loop in place, and it's in its size and everything for the flow, for the pressure going, through the particular loop design, how do you then add on, say you're putting another lab space in or another utility process in, when that flow would be in excess. So because the distribution side of any high purity water system is so flow dependent, your loop is designed to maintain that, that basically consistent flow, it can be very hard to then kind of scale or upgrade that without having to replace the vast majority of your distribution system at that point. So what often happens in this case is you actually just build or put in a smaller subsystem. And what that will entail is, you basically have a tap off of your loop, which will then go to a small storage tank, which will then have its own set of distribution pumps and small treatments, which will then facilitate that particular loop expansion. So essentially, the next system becomes a drop off of your primary loop. That's a good way to kind of maintain your existing system without then having to change all of your loop piping, all of your distribution flow. You simply just putting kind of a subsystem there as a means of treatment. Another question, can you explain why diaphragm valves are sometimes referred over ball valves? This has to do with the cleanliness. Ball valves inherently always trap some amount of water basically around the ball. So when they're utilizing a high purity water system, they mentioned, if you're obviously based on sanitization concerns, ball valves, diaphragm valves are preferable, and they're required in some applications, particularly when you're talking about pharmaceutical or higher grade systems, just as a means to basically prevent even that small pocket of water from building up, from causing some level of overall contamination buildup within your actual system. What are some of the steps used to determine the system water quality? That's really process dependent. It really, determining what your system needs, depending on if it's industrial environment or if it's a higher education requirement, typically depends on what your actual application is. If you're feeding various tools or machines, they'll generally list the water requirements that they're trying to target. And bear in mind that RODI systems, high purity water systems, do not necessarily have to target a specific water quality. They don't want to say, okay, ASTM type 1. There are many ways to use those as basically a base guideline and then modify them as a means to allow you to kind of customize them to your own requirements. So you may see, okay, I have a machine that requires 17 mega ohms, so 17 is your target. We're looking at ASTM 1, but this is really what we're trying to get to. So that's one way to determine that. On the flip side, your incoming water quality, that's generally available from the city. If you're talking about a city water source, if it's a well water or some other source like that, you generally have to have it tested at that point to allow for proper high purity water system design. What kind of access and maintenance is typically required for these types of systems? That really depends on what what your actual system entails. As I mentioned before, one of the biggest things in the system is going to be the DI resin. If you're going to be utilizing that as part of your system, those are consumable and they need to be monitored and they need to be exchanged fairly regularly. Depending upon, and you will monitor that obviously either with a resistivity sensor. They do make low-level conductivity lights. Those can be generally monitored in like the 2 conductivity range. As far as actual maintenance, filters, high purity water filters are generally good for a long period of time. They only change out about a year. So things like the actual, things like the different filters, the UV bulbs will last. They're generally changed out about once a year. And then the actual rebedding of the water softener or rechanging the brine tank. So I mean, they're not the highest maintenance things, but they do certainly have a fair amount of maintenance requirements that need to be reviewed as far as these systems are concerned. Another question, what is the purpose of nitrogen blanketing? Nitrogen blanketing is put on a system. It is a means to basically allow the atmosphere in your high purity water tank to prevent it from dissolving into your water system. Even when you're talking about very high purity water levels, if you even the basic carbon dioxide present in the air above the tank will actually dissolve in, just based on how essentially clean that water is. So nitrogen is basically only used in the cases where you're trying to maintain a very high resistivity to prevent that atmosphere from dissolving into your system. Another question is chlorine dioxide is good for disinfection and sanitizing. I have not personally used chlorine dioxide in the high purity water system. I think it might be too aggressive in that case. I have used different other types of systems, but you want something that leaves very little chemical residue when doing the different sanitization. So generally ozone or peroxide are the more common, but I'll have to definitely investigate that as well. The reject water from the RO filter, which is called concentrate, has been described by plumbing designers as aggressive. It isn't particularly aggressive. It's basically just concentrated city water that's basically been softened and dechlorinated. So while it has a very high level of ionic content in it, it's not particularly aggressive by comparison to, say, other water sources. So that should not actually be a requirement for these systems. What questions should I ask a client to figure out what type of system they need? That's a very good question. It depends on the type of client that you're addressing. Obviously, this is between basically a plumbing engineer or just a process engineer. And there are a lot of different ways to kind of approach this. The first is that you can look at what type of systems they actually have in their building. Look at how much lab space is actually available, or how much actual space is going to be used for, say, manufacturing in the building. And really from there, you're going to look at which sinks are going to require it, or which fixtures, and that kind of helps you build the flow profile. Then you can kind of break it down. If it's a higher education, you can look at what type of building. Is it chemical engineering? Is it chemistry? Is it biology? That'll generally kind of point you towards specific water qualities. If it's more of a process-based application, they might have proprietary requirements for what they're looking for, or they might have various tools or machines that are going to have a water requirement or water quality that you can really use to build your water quality profile. And this also goes kind of along with another question I have here, which is what is the use of point-of-use filters? We didn't talk much about point-of-use in this. What a point-of-use system is you have essentially a very miniaturized high purity water unit, which is usually located at like one sink or one tool or one machine, and it basically changes the incoming loop water quality to a higher water quality. And this can be very common when you have, one particular lab or one clean room environment that may need a higher grade of water than the rest of your building. You don't want to necessarily have your central plant or primary high purity water system operate in that, so you put in basically a smaller point of use. So that also can kind of play into the overall picture of how you want to actually approach designing your system. And we can certainly talk about that more offline if that's something that would be of benefit to people. And then one last question here. I think we touched on this one before. How does water temperature affect RO performance? The cooler the water, to basically ROs can operate from 40 to 85 degrees. Anything above that is anything higher than that can cause membrane degradation. Anything less than that, the membrane is basically too tight. You generally want to operate these in a level whereby you can, I'd say about 50 to 60 degrees is kind of the optimum range. Higher temperatures will get you higher throughput but lower water quality. Lower temperatures will get you better quality water but lower throughput, which you can adjust by increasing the pressure on your actual system. All right. I think we are past our time at this point, and so I want to thank everyone for joining. If you have any more questions, certainly feel free to reach out. I want to thank everyone who joined today, and again, we will be sending out a survey as well as a copy of this for people's viewing. And with that, I want to thank everyone, and have a good day.